All right, here we are back for part 2 of section 3.3. So here we have a table and they're asking us to interpret two different things. And then down here, they actually added a context for us. So our input for the function is minutes. Our output is a number of miles. So f of 60 is here. So after 60 minutes, it's at 50 miles. Like, I don't know more of the context to know what it is, but this is telling me at 60 minutes, 50 miles. Those go together. All right, cool. Now we're looking at F inverse of 60. That is going to be here and there. So the inverse, this 60 is now miles. So at 60 miles, it's at 70 minutes. So it's just that whole input output, what the notation means. So here the numbers were picked to kind of be confusing, like the number of minutes and the number of miles. Like there's some numbers that are the same in the table. It's not a consistent thing. So whoever was driving here, it wasn't a consistent speed the whole way, which is actually normal. But for us, it's just practice on interpreting that based on what we're given. All right, now we've got same song, second verse with looking at a graph and then talking about its inverse. So G of 3 is when X is 3. What is our function value? So G of 3 is 1. So I could also say that this means G inverse of 1 is 3. They didn't ask us for that. I'm just kind of extending what we already know. All right. G inverse of 3 is a different place. All right. So now we're going to go G inverse is when 3 is the output. What is the associated original input? G inverse of 3 is 5. So this tells us that G of 5 mapped to 3. So it's talking about two different locations on the graph. But based on which function they're talking about, or they're talking about the function or its inverse, changes how we look at the graph, where we start versus where we're going to. Okay, so here is the lovely list of steps for finding an inverse. These two steps can be interchanged. That is the way I learned it. That's the way most math teachers I know learned it. And that's just because solving for y is something that you do a lot more of, especially when you're looking at equations of lines and you're going to graph them. First step is solve for y. So you get really used to solving for y. Here, they solve for x. And that's just, I mean, when you're solving equations, you're solving for x, so I guess that makes sense too. But either way is acceptable. I'm not going to force you to pick one or the other. So there's that. So example 8 is a very disgusting fraction, and it wants us to solve and find the inverse. All right, so I would like to have notation that's not f of x, so that's why our first step is trade that out for a y. So y is 2 over x minus 3 plus 4. All right, so if I'm following the steps in the book, you know what? The book would have it that way. I'm going to do it my way where I swap them and then solve. The thing is, whichever way you do, make sure you only do the swap the letters once. So in place of y, I'm going to write x. And then in place of x, I'm going to write y. All right, now I want to try to get that y by itself again. So I'm going to minus 4 from both sides as my first step. So we have x minus 4 equals 2 over y minus 3. All right. And just because I'm going to have to write other stuff down here, I'm just going to recopy that up here. Okay. Here's where it gets weird. So I need that y to not be on the bottom anymore. But it's not just y on the bottom, it's y minus 3 on the bottom as its own, like, binomial. So what we're going to do next is multiply by that thing on the bottom. We don't want fractions anymore. So over here, I'm going to multiply by y minus 3. Now that means I am multiplying by it to the whole side. So what I have on the left now is technically it looks like the start of a FOIL. Do not FOIL it. So just like gut reaction, don't do it. We're going to leave them like that. So I have y minus 3 times x minus 4 is equal to 2. Now I'm going to get that x minus 4 and divide it away because it's not helping me get y by itself. So we're going to divide both sides by x minus 4. But if we had multiplied it out, then we would have had the y in more than one spot and the x in more than one spot, and it would be really confusing. So we do this. Now we have y minus 3 is 2 over x minus 4. And our last step is going to be moving that minus 3 by adding it to both sides. So this would be y equals, so I'm just going to skip ahead to writing f inverse of x equals 2 over x minus 4 plus 3. So looking at my inverse, I can see that x equals 4 is a domain restriction. If I plugged 4 into this, I would divide by 0, it would be bad. That means for our original function, 4 is a range restriction. It means the y values will never hit 4. And if you look at the equation, 2 over x minus 3 normally has a horizontal asymptote of the x-axis, y equals 0. That plus 4 takes that and moves it up 4. That's the x minus 4 we're seeing in the denominator now. Because in our inverse, it becomes a domain restriction. So if you graph a rational function and then find its inverse and graph it, what you see is the things that were vertical asymptotes become horizontal, and the things that were horizontal asymptotes become vertical. So over here, the x minus 3 that we would have in the original function, so x equals 3 is a domain restriction. That's going to be a range restriction in our inverse. And then look, plus 3. The same way the plus 4 was working in the original function, the plus 3 works in this. So there are algebraic ways of figuring out range restrictions, but when the functions start getting a little uglier, that's why we used to find the inverse. Nowadays, you can quickly graph things, so looking at the graph makes more sense, but none of us math teachers learned it that way, so we don't do that. We probably should. And that's, I'm sure, something we will hopefully do in the future. All right, almost done with this section. So this guy here, same song, second verse, we're finding an inverse with radicals. So put our y. And I'm going to go ahead and swap them, just that is my habit. Or if you look at the book is going to go through the steps where it gets x by itself and then swaps them. It doesn't matter which way you do it, you'll end up with the same result. Minus the 2. So we have x minus 2 is the square root of y minus 4. All right, now I want to get rid of a square root. So I can square both sides. And hopefully this sets off like a mild, like, is that going to work out? In this direction, yes. If there was a plus or a minus, the square would get rid of it. What we're going to see later is that our original function has a domain restriction. And we're going to have to chase that restriction over into the inverse as well. So where part of the inverse we're not going to consider because our original graph didn't have points there. All right, and I'm just going to leave it x minus 2 squared. I don't want you to multiply that out. I don't want to know what it is right now. Go figure. Digital pen, that shouldn't do anything, and yet it does. And then we just add the 4. So f inverse of x is quantity x minus 2 squared, and then a plus 4. So the original is a radical that's been shifted right and then up, but it only has a domain from 4 to infinity. So our inverse here, we need to restrict the domain so it matches that. So the range restriction on this original square root function is our domain restriction that we need on this quadratic. So the range restriction is a little bit weirder. All right, so this would go 4 to the right and 2 up, and it starts at that point and goes up to infinity. So our range here, range of f is from 2 to infinity. And then when I look, x minus 2 in parentheses, so 2 is the number that makes that 0. That is our vertex, like the x coordinate of the vertex. So that is where we normally chop a parabola in half when we're talking about inverse functions. So we'll have our inverse, but we're going to add restricted to 2 to infinity, or we could say x is greater than or equal to 2. All right. So this whole idea of like, where was the function defined? So what is the inverse going to look like? We're going to play around with that when we do the trig functions. So I've just got this one more. So remember I talked about it's inverses swapping x's and y's. On a graph, we can see that happen by reflecting across the x equals y line, or y equals x line, which is the perfect diagonal. So if I have a graph like here, like this, when I flip it across the inverse line, it's really hard to do on the screen. But like, it's weird, but basically you draw the diagonal, treat that diagonal like a mirror, and then try to draw the mirror image of your original function. So here, f of x is the square, f inverse is the square root function. So between 0 and 1, the original graph, when we square fractions, we actually get smaller results. So that's why it's below the y equals x line. And that's why the square root is slightly above the y equals x line, the mirror image. Well, 1 maps to 1 on the original function, so the inverse of 1 maps to 1 on the original function. So they share a point there. And then our original function, 2 squared is 4. So in our inverse function, 4 inverted will map back to 2, or the square root of 4 is 2. So you can get a rough sketch of an inverse just looking at the graph and then reflecting it. And a lot of times you can do that just by reflecting the nice points you see and then just doing a rough sketch. And that's what we're going to do here in our last example for this section. So this here is, we haven't talked about it much, but this is the graph of probably log base 2. Just because it's going through 2, 1, and then it's going through 4, 2. Yeah, this is log base 2 of x. So the inverse of that is 2 to the x. But just look at our points. So this is going through 1, 0. So our inverse will go through 0, 1. This goes through 2, 1. So our inverse will go through 1, 2. This goes 4, 2. So our inverse will do 2, 4. And then over here, negative 1 looks to be about a half. And all the rest just get closer and closer to the axis. So there is our rough sketch of the inverse. So if I look, there is our y equals x line. And there is my shaky drawing of the inverse. But you could see the point by point flip back and forth. So the last thing is just this thought of, are there functions that are their own inverses? Yes. The first one is what we call the identity function, which is just x. So if f of x equals x, and I compose it with itself, f of x is still just going to go to x. So just be like 1 goes to 1, and then 1 still goes to 1. So this function doesn't do anything to our number. What we put in is what we get out. So that's why it's called the identity function. Now, if your brain is like, but we called like 1 the multiplicative identity, and we called 0 the additive identity. Yes, this is the identity function. You can actually think of functions in the same way you can think of numbers, and then you're getting into modern algebra. So if that thought is like, ooh, that sounds cool, hey, future crazy math, have fun. All right, the other function that does this is 1 over x. So I'll just call that g, but whatever. So if I do 1 over x, I multiply by the reciprocal, so I end up back at x. So 1 over x is its own inverse. And then there's another one where we have c minus x. So if I nest that together, I'll end up with minusing the x. So I get a positive x out of the composition, and then the c's will cancel each other out. And what you end up with is c minus x is a perfect negative slope line. Where this is the c value. But if I put perfect positive diagonal, the line, when I flip it, is itself. Our perfect diagonal line is the identity function, the f of x, y equals x. And then 1 over x, when you look at it, it has this behavior where the two positive parts, like they're a nice mirror image across the diagonal, and the two negative parts do the same thing. All right, so there are other functions that we can draw that would be their own inverse, but they're going to exhibit like, they might be on the line. The points may be like the c minus x, so, All right, so that's the end of 3.3, and then I will record inverse trig functions.